Dear students, having learned about this activation energy, what is activation energy, what is the effect of activation energy, how we define activation energy, Arrhenius equation, threshold energy. Now we'll go through catalyst. What is the effect of catalyst? How this catalyst plays a role in a chemical reaction? So then we'll go to the application of the catalyst, Arrhenius equation in solving problems. So coming to the catalyst, catalyst is a chemical substance which is used for enhancing the rate of a chemical reaction. During the course of reaction, this catalyst participates but does not undergo any chemical or physical change in its state. Now, this substance participation reaction and this forms a transition state with the substrate, and finally this is converted into the products. So during the course of reaction, this catalyst provides an alternative pathway by which the activation energy of the chemical reaction is decreased. As the activation energy of the reaction is decreased, the rate of chemical reaction is increased. So normally when we talk about this catalyst, we simply say the one which increases the rate of a reaction. So considering this, we have this catalyst. So these catalysts, suppose we have a reaction in which the reactant R is to be converted into product P. So for this reaction, suppose the reaction is carried out in absence of catalyst. So in absence of catalyst, suppose this reaction rate constant may be K1 and its activation energy is suppose EA, that is absence of catalyst. The same reaction is carried out in presence of catalyst, that is uncatalyzed. If the same reaction is carried out in presence of catalyst, suppose the rate constant is K2 and the activation energy of this reaction in presence of catalyst, let this be ESC, where C stands for catalyst. Both the reaction is carried out at the same temperature. Now, same reaction at this temperature, absence of catalyst, rate constant K1, activation energy E. In presence of catalyst, activation energy is ESC, rate constant is K2. Now, we have Arrhenius equation, so therefore, from Arrhenius equation, it says A is equals to A, the exponential fraction, exponential raised to the power EA by RT. So for these two reactions, we can write down absence of catalyst, rate constant is K1, so we have A EA by RT. In presence of catalyst, the rate constant is K2, so is equals to A exponential minus EAC by RT. So we have these two equations, that is equation 1, this is equation 2. Now, taking ratio of these two, now equation 1 divided by equation 2, or equation 2 divided by equation 1, or you can take this equation 2 divided by equation 1. So we have K2 by K1 is equal to exponential minus EAC by RT divided by exponential minus EA by RT, or we can say K2 by K1 is equal to exponential minus EA by RT into exponential EAC by RT, or therefore this is equal to exponential 1 by RT EA minus EAC. So taking logarithm of this equation, we have ln K2 by K1 is equal to EA minus EAC by RT, or we can say logarithm of K2 by K1 is equal to EA minus EAC by 2.303 RT. So if you look at this equation, is similar to that of Arrhenius equation in two different temperatures. Instead of this, we are having one in absence of catalyst, the other one in presence of catalyst. So this is how we can use this equation to find the value of the constant K in absence of catalyst or in presence of catalyst, or if the reaction is carried out in presence of catalyst. So during this course of reaction, if there is change in activation energy, then how the rate of reaction is affected. So this is the use of Arrhenius equation in the reactions involving catalyst. Now this catalyst is of two types. One is known as positive catalyst, the other one is known as negative catalyst. So when we talk about positive catalyst, so these are the catalysts which increases the rate of the reaction, whereas the negative catalyst is the one which decreases the rate of the reaction. So positive catalyst which increases the rate of reaction decreases the activation energy of the reaction. If the activation energy is decreased, the rate of reaction is increased. Whereas on the other hand, we have a positive catalyst. So negative catalyst. So negative catalyst increases the activation energy of the reaction. So if the activation energy is increased, the rate of reaction is decreased. So considering this, is we say so catalyst so one is positive, the other one is negative. So these positive catalyst increases the rate of reaction. These positive catalyst which increases the rate of reaction. So rate of reaction is increased provided the activation energy is decreased. So this decreases the activation energy of the reaction. Whereas in case of negative catalyst, this is just opposite. So negative catalyst decreases the rate of reaction. If the rate is decreases, that means it increases the activation energy of the reaction. So graphically, this can be represented as, so in case of positive catalyst, suppose this is the reaction, this is the product, this graph, this is absence of catalyst, this is in presence of catalyst. Dotted line represents the presence of catalyst. This represents absence of catalyst. This is reactant, this is product. This is activation energy in absence of catalyst. This is activation energy of forward reaction in presence of catalyst. This difference. So therefore look at this. In absence of catalyst, we have a larger activation energy. In presence of catalyst, the activation energy is decreased. Whereas in case of negative catalyst, this is potential energy versus progress of reaction. In case of negative catalyst, suppose we have this, the reactant, this is product. Now, in presence of catalyst, this activation energy is increased. So this is the activation energy in absence of catalyst. This is activation energy in presence of catalyst. So negative catalyst increases activation energy, which decreases the rate of reaction. Positive catalyst decreases activation energy and correspondingly increases the rate of the reaction. So this is positive and negative. Now the question is, though we are using a catalyst, whenever we take a catalyst and we simply mean that this is a positive catalyst which suppresses the activation energy such that rate of reaction is increased by some factors. Now during the course of this reaction in this catalyst is used, how does this catalyst changes the thermodynamic parameters or equilibrium state or the equilibrium concentration, etc. So these catalysts, so the most important point to remember is catalyst does not affect thermodynamic parameters. Does not affect thermodynamic properties or parameter like delta H, delta G. So enthalpy of reaction is not affected by use of catalyst. Similarly, free energy change delta G is not also affected by the catalyst. Second, this catalyst does not alter the equilibrium state of the reaction. Suppose we have a reversible reaction that is an equilibrium state. If we use the catalyst in this equilibrium state, so the equilibrium state will not be changed by the use of catalyst. The only thing that catalyst plays is this catalyst helps in establishing the equilibrium faster. If the equilibrium is achieved in a faster rate, that means this catalyst increases the rate of forward reaction as well as backward reaction by same amount. If both the reaction is increased by same amount, that means equilibrium will be achieved faster. So use of catalyst does not alter the equilibrium state. If the equilibrium state is not altered by use of catalyst, that means this catalyst does not alter the equilibrium constant also. That means this equilibrium constant, which is defined as rate constant of forward reaction divided by rate constant of the backward reaction. So if the rate is increased by same factor, then this equilibrium constant is defined as rate constant by forward divided rate constant for backward reaction. So both reaction is increased by same factor, so equilibrium constant will not be altered by use of this catalyst. So equilibrium is not altered. If equilibrium is not changed, equilibrium constant remains unaffected, and these thermodynamic parameters like enthalpy change or free energy change is not also affected by use of catalyst. So these catalysts decreases the activation energy of forward as well as the backward reaction. So by this, the rate of forward reaction as well as rate of backward reaction is increased. Now, both rate of forward and backward reaction in an equilibrium state is increased by the same factor. So this results in same equilibrium constant or same equilibrium state. And if the equilibrium state is not altered, that means the equilibrium amount of the reactant species will also not be altered by use of this catalyst. So the only thing this catalyst provides an alternative pathway by which the activation energy of the reaction is changed. If the activation energy is changed, the rate of reaction also changes. So this is the catalyst, and how this important points of catalyst and how this catalyst changes this activation energy. So after this is brief idea about catalyst. After this, let's discuss some problems in which we have to use Arrhenius equations. So let's start with some simple examples. Now let's suppose we have a reactant R changes to product P. This conversion of a reactant to product occurs in 3 steps. Means this is a complex reaction in which the reaction is taking place in 3 steps. So step 1, step 2 and step 3. These are 3 different steps. Now for this step 1, the rate constant is K1. For this reaction 2, step 2, rate constant is K2, and for this step 3, rate constant is K3. And for this first step, activation energy E1, let's suppose this is 60 kilojoule per mole. For this second step reaction, let's suppose this is E1, this is EA2, let's suppose this is 20 kilojoule per mole. And for this third step, let's suppose this is activation energy 3, and let it be suppose 40 kilojoule per mole. So we have this rate constant K1, K2, K3 and their corresponding activation energy. Now the overall rate constant for this reaction, this is given as K1, K3 divided by K2. So this is the overall rate constant for this reaction. Now the question says what is the overall activation energy for this reaction. So question says a reaction occurs in 3 different steps, and K1, K2, K3 the rate constant for the 3 different steps, and activation energies are given as 60, 20 and 40 kilojoule. The overall rate constant of the reaction is K1, K3 divided by K2. Then what is the apparent or the average or the overall activation energy of the reaction? Now we have to use Arrhenius equation. So we have this Arrhenius equation which says K is equals to exponential exponential factor A into exponential minus EA by R T. So we have these 3 different steps. For we have this K1, K2, K3. Therefore look at this. K1 is equals to A EA1 by RT. K2 is equals to A exponential minus EA2 by RT. K3 is equals to A exponential minus EA3 by RT. So we have this K1, K2 and K3. Now K3 is given as K1, K3 by K2. So we have this K1 A1 is A exponential minus EA1 by RT. A3 A exponential minus EA3 by RT divided by K2 A exponential minus EA2 by RT. So therefore look at this. Exponential P exponential factor A exponential. So this is E A minus EA1 by R E. Let's say this. So 1 by RT minus EA1 minus EA3 plus EA2. So this equals to A exponential minus 1 by RT. So EA1 plus EA3 minus EA2. So this value is equal to total activation energy of the reaction. So there is a relation. If the rate constant is multiplied, then activation energy is added. If the rate constant is divided, then activation energy is subtracted. So therefore, look at this is equals to A exponential minus 1 by RT. EA1 is 60, EA3 is 40, EA2 is 20. So this is equals to A exponential 100 minus 20 at T. So minus 80 by RT. So therefore look at this. Total activation energy of the reaction is equals to 80. So this is how we use Arrhenius equation for solving this type of equation. So this is one of the question. Let's go for some other problems also. Question number 2. Suppose we have a parallel reaction. Take this parallel reaction. Suppose we have a reaction A giving you product B and product C. Conversion of A into B. Rate constant is K1. Activation energy is E1. Suppose K1 is 1 into 10 to the power minus 2 second inverse. And suppose E1 is 70 kilojoule per mole. Conversion of E into C, the rate constant, let's suppose this is 2. Let's suppose this is 3 into 10 to the power minus 2 second inverse. And let's say this activation energy EA2, that is 30 kilojoule per mole. So we have parallel reaction, their corresponding activation energy and rate constant are given. So question is, what is the apparent activation energy of the reaction? So we have to find the apparent activation energy or the total activation energy for this reaction, in which B is converted into B as well as C simultaneously by this characteristics. So for such type of reaction, activation energy apparent or total is defined as A1 plus A2 divided by A1 plus A2. So these type of equations should be applied in which we have this parallel reaction. So we have K1, E1, K2, E2. Substituting using the values of K1, E1, K2, E2, we get K1 is 10 power minus 2, E1 is 70, K2 is 3 into 10 to the power minus 2, E2 is 30, divided by K1 is 10 to the power minus 2 plus K2 is 3 into 10 to the power minus 2. So this comes out to be, so taking 10 power minus 2, so 70 plus 90 divided by 4 into 10 to the power minus 2. So this cancels out. So this is 160 divided by 4. So 40 kilojoule per mole. So this is how we define apparent activation energy of a parallel reaction, in which activation energies of the corresponding steps and their rate constants are given. This is the second question. Now let's see third question. Question number 3. Suppose we have a reaction A giving you product P. Now this reaction is carried out at two different temperatures. Now the temperature changing from, suppose from 300 to 310 Kelvin. So we are changing temperature by 10 units. On increasing temperature by 10 units, the rate of reaction is just doubled. Rate of reaction is doubled. Then question says, what is the activation energy of the reaction? So we have this temperature changing from, suppose 300 Kelvin to 310 Kelvin. So let's suppose this is T1, this is T2. At this temperature we have this K1, at this temperature we have this K2. So question says rate of reaction just double. That means K2 is equals to 2 times K1. So we are changing temperature by 10 units from 300 to 310 Kelvin. Rate of reaction is just double. Then what is the value of activation energy of the reaction? Now we have to find the value of activation energy for this reaction, in which rate of reaction doubles on increasing temperature from 300 to 310 Kelvin. So we have to find activation energy. So again, in this problem we have to use Arrhenius equation. So Arrhenius equation, which says E is equals to A exponential minus EA by R T. So we have two temperatures. So at temperature T1, so we have KT1 is equals to A exponential minus EA by R T1. And at temperature T2, this is equals to A exponential minus EA by R T2. Now taking this ratio, taking the ratio of these two, so we have KT2 by KT1 is equals to exponential minus EA by R 1 by T2 minus 1 by T1. Or KT2 by KT1 is equal to exponential EA by R 1 by T1 minus 1 by T2. Now taking logarithm of this equation, we get log KT2 by KT1 is equal to EA by 2.303. Taking LCM, we get this T1 T2 into T2 minus T1. So we have this show KT2 by KT1. So KT2 is equal to 2 times T1. So this means log 2 is equal to EA by 2.303. The value of R is 8.314 joule per Kelvin per mole. T2 minus T1. This is T2, this is T1. The difference is 10 into 300 into 301. So we have this log 2. So log 2 is 0.301 into 2.303 into 8.314 divided by this, or 300 into 310 divided by 10. So this is equals to the value of activation energy. So this is by use of activation energy we can solve this problem. So given K1 and K2 are given, temperatures is given, then you have to find the value of activation energy for this the reaction. So this is one question. Next question, question number 4. Question says, suppose we have an alkene plus fluorine in presence of sunlight, we get alkyl fluoride. That means free radical addition of fluorine to alkene, that is free radical fluorination reaction. What is free radical fluorination reaction? Free exponential factor A or Arrhenius factor A, this is given as 2 into 10 to the power 13 second inverse. So this is free radical fluorination of alkene to give you alkyl product, for which free exponential factor A is 2 into 10 to the power 13 second inverse. Question says, what is the value of rate constant K at S T E condition? You have to find the value of rate constant K. What is free radical fluorination of alkane? Now, one thing that we have to keep in mind is, what is free radical reaction? So, point to be noted is, for free radical reaction, activation energy is always 0. So, this thing you have to keep in mind. So, the reaction is free radical reaction. A is given, we have to find the value of rate constant, at standard temperature and pressure condition. So since EA is 0, so we have this Arrhenius equation, K is equals to A exponential minus EA by RT. So EA is 0, so exponential raised to the power something, this something comes out to be 0. So E raised to the power 0 is 1, so therefore K is equals to A exponential 0, which is equals to A. So that means if the activation energy of the reaction is 0, then the rate constant is equals to the free exponential factor. So for this halogenation, free radical halogenation reaction, the rate constant T is equals to A, which is equals to 2 into 10 to the power 13 second inverse. So point is, for free radical reaction, activation energy is 0. Next question. We have a reaction A to B. For this reaction, suppose question says activation energy of forward reaction. Suppose this is 19 kilojoule per mole, and the activation energy for the backward reaction. Suppose this is 9 kilojoule per mole, and the potential energy of the reactant A, this is given as 12 kilojoule per mole. So we have the reaction for which activation energy of forward reaction and activation energy of backward reaction is given, and the potential energy is given. So question says find the enthalpy of reaction first. The second says what is the threshold energy of the reaction. Threshold energy. And then also says what is the potential energy of the product. Potential energy of the product. So we have to find this. What is delta X? What is threshold energy? And what is the potential energy of the product? Now for this again we have to recall Arrhenius equation. Suppose this is the reactant A, this is product B. This is activation energy of forward reaction. This distance is activation energy of backward reaction. This distance is delta H. This distance, this is potential energy of A. This distance is potential energy of product B, and this distance, this is what we call as threshold energy. So activation energy is given, potential energy of creatine is given. We have to find this value, we have to find this value, and we have to find this value. So we have this first. So enthalpy of reaction is to be defined in terms of activation energy. So look at this. Enthalpy of reaction is activation energy of forward reaction minus activation energy of backward reaction. So we have these values. So forward reaction is 19, backward reaction is 9. So this is 10 kilojoule per mole. So this is the activation energy of enthalpy of the reaction. Second is threshold energy. So look at this, threshold energy is potential energy of reactant plus activation energy of forward, or potential energy of product, which is also plus activation energy of the backward reaction. So threshold energy is potential energy of reactant plus activation energy of forward, which is also equals to potential energy of product B plus activation energy of backward. So taking this threshold energy, which is equals to potential energy of reaction is 12, activation energy of forward reaction is 19. This is 31 kilojoule per mole. So this threshold energy is also equals to this value. You take this third question. Threshold energy is also equals to potential energy of product B plus activation energy of backward reaction. So therefore, potential energy of product B is equals to threshold energy minus activation energy of backward reaction. So threshold is 31, backward reaction activation energy is 9. So we have this 21 kilojoule per mole. So this is question next. Let's go for next question. Question number 6. Question says activation energy of a first order reaction given. Suppose we have a this reaction A changing into product B. This is first order reaction. The reaction is carried out at a temperature of 750 Kelvin. The activation energy for this reaction is 187.06 kilojoule per mole, and Arrhenius parameter A, this is given as 1.97 into 10 to the power 12 second inverse. Question says, what is the value of rate constant and the half-life of this first order reaction? Activation energy and T is given, temperature is given, we have to find the value of T, and for the same reaction again we have to find the value of half-life. So question says K is required, E and A is given, so we have again Arrhenius equation which says K is equals to A exponential minus EA by R T, or the logarithmic form says log K is equals to log A minus EA by 2.303 R T. So therefore look at this, we have this log K is equals to log A log 1.97 into 10 to the power 12 minus E is 187.06 into 10 to the power 3 for this kilo divided by 2.303. R is 8.314, temperature is 750 Kelvin. So we have this, let's suppose this value is A, then A is equals to NT log A. Let's suppose this value is equals to B. So we have this. Now we can look at this. We have to take the logarithm, then again we have to take the logarithm to find the value of K. Now we have this value of K that is equals to B. Question says reaction is first order kinetics. So for first order kinetics, half-life of a first order reaction is 0.693 by T. So we have the value of K here. Substitute the value of T and we will find this half-life. So this is half-life. A is given as second inverse, so therefore the unit of K should be second inverse, so therefore the half-life should be second. This is how we define rate constant K and its half-life. Next question. We have a reaction. 2NO2 gas changes to be 2NO plus oxygen gas. This is a reaction. Now, for this reaction, activation energy is given as 110 kilojoule per mole. Now, at 400 degree centigrade, the rate constant K is given as 7.8 mole per liter per second. This is the rate constant K at temperature 400. Then question says, what is the value of rate constant K at 430 degree centigrade? So we have this reaction. For this reaction, activation energy is given. Temperature is that is the T1. So this is K1. This is T2. Then this is K2. Temperature T1, T2 is given. K1 is given. We have to find the value of K2. We have this A. So taking the help of Arrhenius equation, logarithmic form. So we have log KT2 by KT1 is equals to EA by 2.303 or 1 by E1 minus 1 by T2. So therefore, log KT2 by KT1 is equals to E is given here 110 into 10 to the power 3 divided by 2.303 8.314. This is T2 minus T1 by T1 T2. So T2 minus T1 is difference is 30. So 400 plus 273, that is 673 into 703. 430 plus 273, 703. So this is a pure mathematical quantity. We have K2 we have to define, K1 is given. So therefore look at this. Suppose this value be again A, this value is A. So therefore A E2 by A E1 will be equals to A log of A. We have K1, so we have to find the value of K2. So therefore K2 is equals to KT1 into NT log of A. So KT1 is 7.8 to this unit into NT log of E. This is the value of rate constant K2. Next question. Again, as usual, we are having a first order reaction A, B. The reaction is carried out in presence of catalyst and in presence of catalyst. This is first order reaction. And for this first order reaction, activation energy of the reaction in absence of catalyst is 60 kilojoule for absence of catalyst. This reaction is carried out 300 Kelvin. Now, in presence of catalyst, activation energy decreases to 50 kilojoule. So, activation energy in presence of catalyst, this is 50 kilojoule per mole. The question says, how many times the rate of reaction changes in presence of catalyst at the same temperature? So, let's suppose the rate constant is K1 for its absence of catalyst. The rate constant in presence of catalyst that will be K2. The question says, what by how many factors rate of reaction changes in presence of catalyst? So again we have to take the logarithmic equation of Arrhenius equation. So we have this log K2 by A1 is equals to activation energy in absence of catalyst minus activation energy in presence of catalyst divided by 2.303 R T. So log A2 by A1, E in absence of catalyst is 60 minus 50 into 10 to the power 3 divided by 2.303 into R is 8.314 into temperature is 300 Kelvin. So therefore look at this, log A2 by A1 is equals to 10 into 10 to the power 3, 10 to the power 4 divided by 2.303 into 8.314 into 300. So this is the ratio of log K2 by K1. So let this ratio be A. So therefore K2 by K1 is equal to N3 log of K. So therefore P2 is equal to K1 times N3 log of K. This is the ratio, means this is the factor by which rate of reaction is increased on decreasing accuracy energy in presence of catalyst. So next question, we have a first order reaction A to B. Let's suppose this is first order reaction. For this first order reaction, the value of activation energy, this is given as 98.6 kilojoule per mole, and free exponential factor for this reaction is given as 4 into 10 to the power 13 second inverse. Question says, at what temperature half-life of the given reaction is 10 minutes? Half-life is given, then what is the value of temperature? Means we have this first order reaction with this activation energy and the exponential factor. So question says, when the half-life of the reaction is 10 minutes, so what should be the temperature? Means at what temperature the half-life of the reaction should be 10 minutes. Question says reaction is first order. Half-life is given. So half-life of the first order reaction is equal to 0.693 by K. So therefore K, rate constant K, is equal to 0.693 divided by half-life. Half-life is 10. So this is 10 minute inverse. So we have this rate constant K, activation energy and P exponential factors. We have to find the value of P. Now taking the help of Arrhenius equation, logarithmic form, so we have log K is equal to minus EA by 2.303 RP plus log K. So we have K value is given, E is given, R given, constant K given. We have to find the value of P. So we have log K let's rearrange this. So log of K minus log K is equals to EA by 2.303 RT. We are doing this operation. So therefore P is equals to EA by 2.303 R into 1 by log A minus log K. We have activation energy given. R is a gas constant 8.314. We have log A value is given. We have activation energy, that is given. K, we have this value. So substitute the values of A, K, E and R, will get this temperature. Now this temperature should be in terms of Kelvin. So this is how we define temperature at which this parameter should be satisfied for this first order kinetics. Here are some more examples. K for a given reaction, rate constant K for a given reaction is 3 into 10 to the power minus 4 second. Activation energy for a given reaction is 104 kilojoule per mole. The exponential factor K for the reaction is 6 into 10 to the power 14 second inverse. This is at a particular temperature. The question says calculate the value of rate constant K at temperature tends to infinity. That means this is at a given temperature, we have these characteristics. Now question is, now we are increasing temperature to very large, that is infinity. So at this infinity, what is the value of rate constant K? So again we have to use Arrhenius equation. So Arrhenius equation says K is equals to A exponential minus EA by RT. So we have looked at it, EA by RT. So temperature tends to infinity. So we have this EA by R into infinity. Something by infinity is 0. So therefore look at this. Exponential minus EA by RT is equals to E0. E0 is equals to 1. So that means K at temperature tends to infinity is equals to A. So A value is given. So when temperature changes, it reaches infinitely large value, the rate constant K is equals to the pre-exponential factor A. So this is equals to 6 into 10 to the power 14 second inverse. This is when temperature changes to infinitely large value. Let's go to another equation. For a given reaction A to A, the activation energy of the reaction is 0. Question says, for a given reaction, activation energy is 0. The rate constant K for the reaction is 3.2 into 10 to the power 4 second inverse at 300 Kelvin. So at 300 Kelvin, rate constant for this reaction is this given. Question says, calculate the value of rate constant at 300 Kelvin. So find the value, suppose this is K1, so this is T1. Now find the value of rate constant K at temperature 330 Kelvin, that is T2. K1, we have this is T1, this is K2, we have to find. T2 is given as 330, and for this reaction, activation energy is 0. Now with this characteristic, again we have to use Arrhenius equation. So Arrhenius equation says K is equals to the exponential factor A exponential raised to the power E by R T. So for this reaction, activation energy is equals to 0. So therefore look at this is equals to A exponential minus 0 by RT. So 0 by something is 0. So this is A raised to the power 0. So A raised to the power 0 means we have A. So look at this. If the activation energy of any given reaction is 0, then rate constant is independent of the temperature. So activation energy equals to 0, rate constant is equals to the exponential factor. So this is independent of temperature. So therefore, whatever we change this temperature by any factor, if the activation energy is 0, rate constant will remain constant. So therefore, K2 at 33 Kelvin is equals to K1 at 300 Kelvin. So therefore, K2 is equals to K1, which is equals to K1. So K is independent of, so this is 3.2 into 10 to the power 4. So activation energy being 0, rate constant is independent of temperature, or in the previous question, temperature T changes to infinity, and if temperature infinity, then this exponential term comes out to be 1. Activation energy 0, again this exponential term comes out to be 0. Then constant K is equals to the exponential factor A. Another question, we have two equations. A tends to B. For this, rate constant K1 is given as 10 to the power 15 exponential minus 2000 by temperature T. Another reaction C2D, rate constant K2 is equal to 10 to the power 14 exponential minus 1000 by T. Question says at what temperature K2 is equal to K1? At what temperature K1 equals to K2? So for this rate constant K1 equals to K2 at a certain temperature. So what is the temperature? With this. So K1 equals to K2 means these two values should be equal. So therefore 10 to the power 15 exponential minus 2000 by T equals to 10 to the power 14 exponential minus 1000 by T. So this is 10 to the power 15 divided by 10 to the power 14 equals to exponential 2000 minus 1000 by T. So this is 10 exponential 1000 by T. Taking logarithm, we say log 10 is equals to 1000 T by 2.303. So log 10 is 1. So that is log 10. So this is 1000 by T. So log n is 1. So therefore 2.303 T is equals to 1000. So therefore temperature T is equals to 1000 by 2.303. So this is Kelvin. So at this temperature, both rate means K1 should be equals to K2. Means nothing but this, you have to just equate the relation and solve the below T. Question says, find the percentage of reactant molecules find the percentage of reactant molecules crossing over energy barrier energy barrier at 325 Kelvin given delta H of reaction is 0.12 kilocalorie per mole and activation energy of the backward reaction this is given as 0.02 kilocalorie. So we have a given reaction for which delta is given as this value. Activation energy of backward reaction is given as 0.02 calorie. Temperature is 325. So at this temperature, how many molecules or the percentage of molecule that has crossed this energy barrier? That means this percentage of molecule is likely to be converted into the product. So find the percentage of that is molecule crossing over this energy barrier. So we have this equation from Arrhenius equation. A is equals to A exponential minus EA by R T. So this term exponential raised to the power minus EA by RT, which is known as Boltzmann factor. So this Boltzmann factor is nothing but the fraction of molecule or the percentage of vacant molecule which is crossing the energy barrier. So this is a fraction of molecules having energy equals to EA or greater than EA. So this is the percentage of molecules. So we have to find this value. Now for this we require is activation energy, but activation energy of backward reaction and enthalpy is given. So we have to use this relation between enthalpy and activation energy. So enthalpy of reaction is activation energy of forward minus activation energy of backward. So therefore activation energy of forward reaction is delta H plus activation energy of backward reaction delta H is 0.12. This is 0.02 kilocalorie. So this is 0.14 kilocalorie per mole. That is activation energy of the forward reaction. Now we have looked at this exponential minus EA by RT. So we have the value of EA, temperature is given, R is a constant, so we have to find this value. So therefore, percentage of molecules is equal to exponential minus EA by RT. So let us say X. So therefore, X is equal to minus EA by RT. Taking logarithm here, log X is equal to minus EA by 2.303 RT. So where this activation energy of forward reaction is 0.14 kilocalorie. So 10 per 3 divided by 2.303. Now unit of energy is given in terms of calorie. So in terms of calorie, the value of R is 2. You have to use this 2 calorie. So this is the value of log X. So let this value of log X be suppose some minus D. So therefore X, this is nothing but the fraction of molecules. So this X is equal to NG log of minus D. This is the fraction of molecules crossing this energy barrier at this given temperature. So fraction of molecule is nothing but this Boltzmann factor, which is exponential raised to power minus EA by R. You have to find this fraction. Question says a reaction that is A to B, which is a first order reaction. Now for this first order reaction, half life is 6.93 into 10 to the power minus 3 minute at 300 Kelvin. Half life of this first order reaction is this at this temperature. At this temperature, at this same temperature, 10 to the power minus 8% molecules able to cross energy barrier. Molecules crosses energy barrier. So reaction is first order. Half-life is given as this will have this percentage of molecules crossing energy barrier is 10 to the power minus 8. Question says find the value of A. Calculate the value of A. Is three exponential factor or the collision frequency. So question says look at this fraction of molecules crossing over this energy barrier. This term, this is exponential minus EA by RT, that is the percentage of molecule crossing over this energy area. So this is equals to 10 to the power minus 8%. So this is 10 to the power minus 10. So these molecules is crossing over this energy barrier. Half-life of first order reaction, half-life is given, so half-life is equals to 0.693 by K. So therefore, K is equals to 0.693 by half-life. Half-life is 6.93 into 10 to the power minus 3. This is minute inverse. So this comes out to be 0.693 into 10 to the power 3 divided by 6.93 minute inverse. So this is 10 to the power 2. So rate constant is 10 power 2 minute inverse. Fraction of molecule crossing over this energy barrier is 10 power minus 10. Then what is the value of the exponential factor A? So we have to use Arrhenius equation again. So from Arrhenius equation, K is equals to A exponential minus EA by RT. So this value is minus 10. This is 12. So 10 to the power 2 is equals to A into 10 to the power minus 10. So therefore, A is equals to 10 to the power 2 divided by 10 to the power minus 10. So this is 10 to the power. So this is the value of the exponential case. So these are some of the examples or questions in which we use Arrhenius equations with different modifications.